Hi everyone, I'm Luz Angela Garcia. I'm a postdoc fellow at Universidad EXI in Bogota, Colombia, and I'm going to talk about the properties of high redshift galaxies through this theoretical work that I have been doing. The evolution of high redshift galaxies determines the progression of the epoch of reionization. Their hierarchical model for the structure formation provides a scenario where small dark matter halos of around 10 to the 6 solar masses at redshift 30 reach a critical temperature to agglomerate baryons and form stars, initially metal free or POP3. However, these first stars evolve and consume their fuel in short periods and produce the first supernova explosions. With them, the chemical pollution of the intergalactic medium begins, and consequently, a new generation of POP2 stars form and the first black holes in the universe. All this period is known as Dark Ages, and right in the middle and the end of this period, we have what we call reionization. So, interestingly, POP2 stars supply an additional cooling source. Therefore, these structures are less massive and have longer lives than metal-free stars. The interaction of the collapsed systems in the universe and the IGM is described by feedback models that account for winds that spread out the chemical elements and vary the ionization state of the free hydrogen. Once the available neutral hydrogen in the IGM is less than 10 to the minus 4, we consider that reionization is concluded, and we think that it was driven mainly by POP3 and POP2 stars, but also by dwarf galaxies that are too faint to be observed by the current facilities that we have in hand. There is a complex correlation between the anisotropies and the CMB map that come from the primordial Gaussianities and the zones where preferentially forms galaxies, the dark matter overdensities or halos, as seen in this animation. So there is a clear link between the overdensities in the large scale structure and then the regions where the initial seeds were defined in the CMB due to the inflation, and that's the link that I'm trying to make here. And this animation is showing a small volume where we are simulating the progression of the galaxy formation. So let's talk about the simulations. This work relies on a set of high-resolution hydrodynamical simulations at high redshift from redshift 4 to 8. The model is based on a customized version of the smooth particle hydrodynamics, or SPH, code Gadget 3, with especially flat cosmology, lambda CDM, and cosmological parameters from Planck 2015. These models account for a self-consistent star formation and metal enrichment, and two different feedback models to be known as momentum and energy-driven wings by its acronym in the names of the simulations. The fiducial model is the first one that is presented, that is highlighted with the blue box, the CH18 512 MDW, and it doesn't account for molecular cooling. These numerical simulations are supported by a multiphase star formation criteria, self-consistent stellar evolution and chemical enrichment, supernovae momentum and energy-driven wings that I mentioned before, as well as a metal line cooling and a low temperature cooling by molecules and metals. The initial conditions were set at 125. We have molecular and metal cooling, and there's a self-consistent scheme for the metal enrichment. Okay, so in order to characterize the galaxies in the simulations, the first thing I wanted to show is the halo mass function at redshift 8 and 6, as shown in here in light blue and dark blue, and a comparison with the universe machine in dotted lines. I'm just showing the results with the fiducial model, and I'm only including halos with a resolved halo with at least a minimum mass of 10 to the 9.1 solar masses, which is equivalent to about 470 dark matter particles. If the halo accounts for less than that number, it is considered unresolved and is not going to be taken into account. So the first thing that I want to highlight here is that the predicted halo mass function at redshift 8 and 6 are in agreement with the fit presented by Barussi 2020 with a constant power law slope of alpha equals to -2. The number density of halos follows the relation equals to -1, but it's still consistent with our boxes, although the simulations here account for a narrow range of halo masses and are smaller than the ones considered in the universe machine. We can conclude from here that the power law slope is in agreement with a value of -2 at redshifts from 6 to 8. In this plot, I'm showing the halo occupation fraction as a function of the halo mass for the fiducial model. Galactic halos with masses below 10 to the 9 solar masses do not experience efficiently atomic cooling and they are unresolved. Though most of the halo reach a maximum occupation at 2 and 3 times 2 10 to the 9 solar masses at redshifts 8 and 6 respectively. So that's what I'm showing here. And also it's interesting to see that most of the halos have a maximum occupation for the redshifts of interest in here. Now, the number of stars formed inside the virialized halos per beam mass and per moving volume, it's known as the simulated galaxy stellar mass function. I'm comparing with the functional form given by the following equation that is presented in the first paper that I have there, and I'm showing the results from the simulations at redshift 8, 7, and 6 from left to right, and I'm comparing with observations from Song and Gonzalez and different fits that are showing in Badaf-Beukar 2019. All the galaxy stellar mass halo function are consistent with the observations, and interestingly, in particular, the simulations with a box size of 18 megaparsecs over H are well inside the limits defined by the observations, which is quite promising. Then we have the galaxy stellar mass to halo virial mass function. Again, for halos that are considered resolved, it means that they have masses above 10 to the 9 solar mass. We can see that the simulated galaxies follow a trend of 10 to minus 2, and at high mass end, F star moves to 10 to minus 1. However, we have just a few galaxies with that in the high mass end. The evolution of F star grows with redshift, with more galaxies with large stellar masses at redshift 6. This is also consistent with Astreus simulation and the Renaissance results at the high end mass, but it shows at least an order of magnitude discrepancy with the results presented by Beruzzi 2020. Now, the star formation rate is the mass of the new stars in the simulation measured in the total volume per year. It is commonly assessed by galaxy surveys or derived from studies with luminosity functions. In particular, the way that I'm showing here to compute the cosmic star formation rate is by adding up the star formation of each galaxy particle per common volume. And I'm comparing with what is shown in Maddow and Dickinson 2014. And what we see straight away is that the cosmic star formation rate density at this redshift range is the observable limited to masses with luminosity cut of MUP lower than minus 17, or equivalently to a minimum star formation rate of 0.33 solar masses per year. There is an agreement between all the simulations and the results presented by Maddow and Dickinson 2014 and later on by Filkenstein in 2016. And we see that they have the assumption that the mass of heavy metals per baryon density produced over the cosmic history with a given star formation model and IMF average yield of 0.02 is consistent with the predictions from the simulations from 4 to 7. Now, this is the predicted ratio for the simulations for the ratio between the observed MUV and the total cosmic star formation rate in the different realizations that we consider. And although the universe machine that is shown in the blue region shows an increment from redshift 8 to 4, the simulations are mostly flat, and the average goes around 0.4, indicating that luminous galaxies stay pretty much the same, about 40%, compared with the total galaxies that are star forming in this period of time. Then what the results that we discussed before in the star formation rate are also consistent with the chemical enrichment, and they assume that the amount of heavy metals is proportional to the model of the star formation rate, with seems to be in agreement with other observations, the IMF and the stellar yields. So in the simulation, the chemical enrichment is driven by the star formation and is mainly spread through wings that shock heated the gas. So we're gonna have an scheme where metals are spread from the galaxies to the outskirts and the IgM. So we see that there's practically no enrichment in the voids, and most of the enrichment is found in the IgM and CGM. This is a mainly theoretical prediction from our models for the chemical evolution from redshift 8 to 4 with all the models. Interestingly, there is a correlation between the star formation rate in simulations, mainly driven by the feedback processes of the gas and the cosmic mass density of this element. Also interesting is that the different supernova feedback mechanisms played a dominant role in the evolution of the star formation rate and therefore in the chemical enrichment. So the results are very similar for different for all the different boxes with 18 megaparsec over each size, but they differed a bit from different resolutions in our simulations. I leave you with a few conclusions derived from this work, and I'm looking forward to discussing future perspectives to this study. Thank you very much for watching this video. If you have further questions, please contact me via email at lgarciap@exi.edu.co or through my Twitter account at penlua. Thank you very much.